few QR codes. So this one's a QR code for our LinkedIn group, and I put in the links to all the collab sheets. If you go to the LinkedIn group, you'll have access to this sheet, so you can run it. You don't have to install anything. So all the code, everything here, you can run. If you have a Gmail account, you can save your own copy, mess around with it. Everybody gets access to everything we do. And I think, I guess I haven't seen you before. Are you familiar with Colab or Python or anything like that? Or no?
Bit of Python.
Okay, cool. So Colab is really cool. Do you know what the Jupyter Notebook is?
No.
Okay. So Colab is cool. So basically, Colab is a kind of notebook where you can have text and actual code cells you could run, and you can edit them and make changes. So I'm gonna show you the library. We're actually gonna run stuff in it. And with this link, and if you go to LinkedIn, you can have it. I can email you the link if you're not on LinkedIn, just let me know. You'll be able to have like your own copy. You don't have to install anything to run this. You could go straight online, it runs all the codes, you can make changes. Yeah. This is so everybody can follow along and never needs to worry about installing it. Yeah. Hey, have any problems with it, let me know and I'll make sure you'll get hooked up. Awesome, cool. And then if you get a moment, this is for later, but this is just for attendance. So if you get a moment, you can stay. This I'll go to the end of class 2. Just enough math if you want to talk symbolic math. Okay, I think that was Linux. Okay, cool. So, and I'll show you this near the end. That's just our attendance sheet if you want to scan just the attendance form. So, okay, so really quickly, so just enough math. So we're a group that talks about the applications of math topics to programming, how you can use math topics to make your programming or even QA life easier, right? Various tools that you could use, do better algorithms, even avoid doing some extra work. And all of our, we don't really dive too deeply. Well, I've Justin on the line, he tends to dive a little bit deeper, he's a math PhD. I tend to be more like, here's the Python package, here's how you can do it. And all of our stuff is in Python. So everything's in Colab notebooks, it's all in Python, it's accessible to everybody. And really the idea here is to give you just enough math so you can identify problems and have ways of figuring out how to solve them without really having to know a lot of math knowledge, just understanding the concepts. Now, if you have any questions, please stop me. If I'm going too fast, please stop me and I'll be happy to explain anything you need. Okay. And pretty much here, I have a lot of weeds because Justin's on the line with me. So I'm a software developer. Been programming for more years than I can probably remember. And Justin, who's on the line, he's a math PhD. And so we know our stuff, but we're not necessarily experts in a particular set of areas we present. So a lot of times we're learning with you. So this is kind of more collaborative. So if you had any interesting experience around this area, feel free to speak up, let us know if you have any questions. Anything we say is not to be taken as business advice, right? It's like, hey, it's an interesting idea. Sure, try it out, just don't come back to me if something, happens. And all of the opinions expressed are ours and not those of our respective employees. And all the code we write here just for clarity and notebook friendly. So we want you to understand the concepts so we don't worry too much about, oh, we're going to refactor it up to this, whatever. It's more like, let's make it just as obvious, and readable as possible. So let's dive in and talk about symbolic math. So today's talk is about a package in Python called Sympy, okay? And Sympy is a package for doing symbolic mathematics. So symbolic mathematics, and you know what? Let's collapse this. So what is symbolic mathematics and what's the difference between that and regular math? Mathematica? Okay, it's like something Mathematica does, right? If you use Mathematica or MATLAB or GNU Octave, right, it'll do symbolic math. But what is it though? Like what is it that makes symbolic math symbolic? Or what's special about symbolic math that makes it different from the math a lot of us think of as math?
Yes, like generics, equations, solutions.
Okay, good, generics, yeah, cool. And that's right. Does anyone want to add to that?
Visualization?
So you can do visualizations with it. It's not about visualizations, but you can apply visualizations to symbolic math. It'll sometimes help you actually solve equations or even understand some things. So you can use that tool with symbolic math. Yeah. So symbolic math is generally going to involve the use of things like symbols instead of like actual numbers, right? So instead of like, saying 100 plus 20, you'll be looking at things like x plus 20, right? And the reason why it's useful is because you can make broader universal statements, you can solve equations, and you can really solve a whole host of problems and even find ways of simplifying your code when you look at things symbolically, right? And here I'm using symbolic math in a bit of a broader sense. Not only am I talking about things like variables like x, y, and z, but even things like using, like Sympy will even talk about things like fractions, like 1/3 instead of 0.33333. It kind of treats that as symbolic because it doesn't really reduce it down to like a decimal approximation. So you can also like do math and preserve full precision. And you'll see examples of all of this when we get down to it. Does that make sense? Okay. So, oh, you raise a hand. Yes, Justin. You can speak up, you don't have to raise your hand.
But I just don't want to get into like an awkward, thing related to the lag time or something like that. I don't want to I think I'm jumping in at the right time, but then I just end up interrupting you. So I just want to say that I kind of looked at using symbolic math, doing a little bit of research on a matrix. Right, so where I was very interested in the eigenvalues of the matrix, right? So I was trying to use Mathematica to compute like symbolic representations of the eigenvalues, right? Mm-hmm. And I wanted to do it because I had solved for the eigenvalues. I had like formulas for the eigenvalues in the case of a 3x3 matrix, but I wanted to do an arbitrary number of an arbitrary size matrix like 5x5 or 10x10 or whatever. But the reason I wanted to do that was there were two really good reasons to do that. Number one, I was running simulations. I was going to use this matrix to run simulations of a process, and so it would have given me like kind of a computational advantage because in the simulations that I was running, I had to compute the eigenvalues every single time step, and that's computationally sort of expensive. If I had the closed form formulas, it'd be much less expensive, so my simulations would run faster. And then there was also the fact that the process that I was simulating had a certain domain in which it was supposed to happen. Outside of that domain, it didn't make sense. So I wanted to be able but it tended to go. The process tended to move toward the boundary of the domain, right? Or maybe I should call it the state space or whatever. But I was simulating something. The state space was a certain space, and the simulation tended to go towards the boundary. And as it went towards the boundary, the eigenvalues got numerically unstable. So it would start giving me nonsense. It could start giving me nonsense results as I approached the boundary. And so I'd have to recognize that and halt the simulation. But with a symbolic representation of the eigenvalues, the precision would be much better, and so that would improve my numerical stability. So.
Yeah. And I'm glad you brought that up. And I'm going to show like an example where we preserve precision. That's a lot simpler. It just involves numbers. We're not going to deal with matrices or eigenvalues. But I'm going to show an example of that. But when you're able to keep it symbolically, you don't necessarily try to approximate things as you don't get that degrading precision risk, right? Or ultimately that can cause you to either lose precision or even get into some weird areas because again you lost precision.
Yeah, that's exactly the type of problem I was trying to tackle. So this was like a biological. It was a problem in evolutionary biology where like the boundary of the state space meant that a certain species of microorganism was going extinct. And when that happened, there's like this question like, what the heck do we do? Because the matrix starts becoming unstable. Right. Anyway.
Yeah. Cool. Yeah, we're going to see a much simplified example of that here. So, yeah. Cool. Thank you. Yeah. So yeah, so tools for symbolic math, we got a variety of them. So there's actual languages you could use, entire systems that are dedicated to symbolic math. Mathematica, MATLAB, Maple, Octave is free. The rest of them I believe aren't, and of course Sympy, which is what I have here, is free. So yeah, so if you're interested in playing around with entire systems for symbolic math, you gotta go with Octave. The other three are pretty big names, especially Mathematica and MATLAB. So again, we're gonna use Sympy here. And really to use Sympy, we just import the packages, right? If you're using Colab, it's all installed, it's all good to go. And so I just have the packages here. Plus I got a little something that just makes the display a little bit nicer. But really, you just pull it in, this is all you need for Sympy. The rest of this is just support to kind of show you examples. Okay? So over here, so Justin was just talking about precision, right? He was talking about precision and he went into he was pretty deep in math, eigenvalues, eigenvectors, all that fun stuff. I'm gonna give you a simpler example of how precision can be preserved when we work symbolically. So Sympy has a bunch of math functions that are basically the equivalent of the ones that Python already has, but they actually operate symbolically so they preserve precision. So to see what I mean, the math package in Python is how you would normally do a lot of math operations, like square root, right? Math.sqrt is going to give you a square root. Sympy also has a square root function, okay? So I'm going to get the square root of 8 in both cases, okay? I'm going to get the square root of 8, okay? And then I'm going to multiply it by, I'm going to square it and multiply it by 2, right? And I'm going to do it both with the one I get from the Python math package and the one I get from Sympy. And you'll see what's going on here. So I just click here to run the cell. So this is the one that Python first produced. It's an actual math package. They say, hey, what's the square root of 8? It gives me an approximate number, 2.82, etc. I believe the square root of 8 is irrational, so it's a decimal that goes on forever. Okay? No repetition. And so here it is. This is like an approximation of the square root of 8. Now if I take the square root of 8 and I square it, did you have a question?
No. It's interesting.
Okay.
Wow.
So if I take the square root of 8, right, and I square it, I expect to get 8 back, right? I mean, the square root of 8 squared should be 8, right? And so if I take the square root of 8 and I square it and I multiply it by 2, I expect to get 16, right? Square root of 8 squared is 8 times 2 is 16. So here in Python, of course, it gives me an approximation. So when I square this and I multiply it by 2, I don't quite get 16, right? I get a number that's very, very close because it loses precision, right? Now, I did the same thing here with Sympy, and here's the results. When I get the square root of 8, Sympy gives me back essentially a symbolic value. I mean, it's a number, but it hasn't been fully evaluated. It says, oh, the square root of 8 is 2 times the square root of 2. I'm not going to reduce the square root of 2. This is what you get. I'm like, okay. And then when I give it the same function, I'm like, okay, well, you know what? Square this number multiplied by 2. It's like, okay, boom, 16. So you see how it preserves your precision. Does that make sense? And feel free to raise your hand if there's any questions. I'm having to go through this again. Oh, I think that's the sound of Justin raising his hand. Yes, sir.
So I give this advice to my students all the time. When they have to do a complicated calculation, right? They're using the little handheld calculators, right? But there's always some fraction of students that they will, like if it's a complex calculation, they're doing it, a few steps, right? So like on the second or third step, they'll say, oh, I'm getting some really long decimal, and so they'll truncate it, right? They'll just either truncate or round it, and that's going to introduce that's introducing an error that's going to be propagated in different ways down to steps 4 and 5 of the calculation.
Right.
So I tell them, if possible, put it all into the calculator at one time, or if they have like a fancy calculator that can do that, where they can actually put the whole expression in there. Right. So this is really the advantage we're talking about is really like that.
Yes.
It's like the symbolic computation works with mathematical expressions. So it has a way of storing the whole expression that I can just evaluate. If you plug in a few numbers, and you don't have to worry about doing the computation in some inefficient way, it's just going to apply the quickest algorithm to do it.
Correct. Yeah.
If you want some actual concrete numbers out of it.
Yeah, yeah. You can almost think of it as almost a lazy evaluation. Yeah.
Yeah, so that's all. So it's like, it's not going to round anything. I mean, well, it rounds like 16 digits or something ridiculous.
Yeah.
Yeah, so that's all I want to say.
Well, thank you. And yeah, so this is like a simplified sort of example of what he was kind of dealing with, but it kind of gives you an idea of how your precision is preserved. And again, same thing here, like fractions, if you want to create a fraction in Sympy, you could wrap your numbers in integer, or even just call it rational. And again, I'm gonna print these out. So first, 1 over 3. Okay, Python's like, okay, 1 divided by 3. 0.33333 goes up forever, right? It's an approximation. If I say, hey, give me the Sympy integer 1 divided by Sympy integer 3, it's like, yeah, I'm giving you 1/3, I'm not gonna evaluate it anymore, right? I can later tell it I want an approximation, but it's gonna keep it at that level for all math. The same here if I use rational. So if I want to use fractions, I could use like the rational packages or libraries in Sympy, and again, it preserves precision. So far, so good. Now, so with Sympy, you could also give it just variables, just symbols, and have it do things like reduce and so on. So for example here I could say, hey, Sympy, I want to declare some symbols, right? And so I have these two variables, x and y, and I say, hey, give me these symbols and give them the name x and y. You still have to give them the names, right? So even though the variables are called x and y, the names to Sympy have to be repeated, it's x and y, okay? And then basically, and then you can just use these as expressions. So here I'm saying, hey, give me in this variable x and y, give me the Sympy symbols named x and y, and go ahead and calculate out this expression, x times the quantity of x plus 2 times y, and print it out. And then I do something else here with different symbols. See what's going on. So here, again, what we would expect, right? It's like, okay, you gave me symbols, I'm going to give you these symbolic expressions, right? Yeah, x times 2 plus y, that's the expression I can't evaluate it further. I can later tell it to substitute values if I wanted to. Now this guy right here, I made it a point to give these variables different names from their names. I call these variables A and B, but I told Sympy they're called W and R. So the names that Sympy will display are the names that are in these parentheses. Just to keep that in mind, okay? Yeah, so even though I call them A and B, they're gonna be printed out as W and R because that's what I call these names here. I always try to keep the names of the variables and the symbols the same because it helps avoid confusion, okay? And again, you can use these in all sorts of stuff, and we'll see how we can start playing with these actual like symbols. So once I have these symbols, okay, and these expressions, I can actually start doing things like factoring, right? So you can see here that I set expression to x times the quantity of x plus 2y, right? So for instance, let's take a look at the results of some of these. I tell, hey, Sympy, factor out this expression. Well, it's already factored out, right? X times the quantity x plus 2y. It's like, yeah, here it is. I'm like, okay, well, expand it. Okay, notice how it did the multiplication algebraically, right? Sure, x times the quantity of x plus 2y is x squared plus 2xy, right? It just did the math for me. And then I could say, and then of course, I could say, okay, well, print 2 times the expression minus x. Okay, well, x, when it does that, right, it simplifies out, and then I tell it to simplify, again, same thing. And then this final guy, you can see here, it gives me x. Because again, it can do operations on the symbols, okay? And this also works if I use Boolean logic, right? Sympy has a lot of good support for Boolean logic, and we'll see that a little bit more in a bit. But I can use this to try to simplify my Boolean logic conditions, right? So let's look at an example here. I say, hey, x, y, and z are these symbols, right? And then I say, okay, well, here's a Boolean expression. Now, Sympy's going to use the ampersand for and a vertical pipe for or, and then a squiggly for not, okay? So here I'm saying, hey, this expression here is x and y, or not x and z, or not z. And I'm going to say, print out this expression, and then print out its simplification, right? So here's the original expression, right? X and y, or z and not x, or not z. And when I tell it to simplify, it says, hey, this expression here, y or not x or not z, is the same as this expression, right? Now this could be useful if you're writing code you've got a Boolean expression, and it's kind of ugly, and you're like, can I clean it up a little bit, right? You can plug it in here, you can come up with a simpler expression to deal with. Okay, does that make sense, everybody? Okay, cool. Any questions so far? And it'll solve equations for you too, right? You can work with things symbolically, but it'll also solve equations. So here I give it another equation, right? X squared minus 3y. And then I tell it, okay, print out the equation, x squared minus 3y. And then I say, okay, solve the equation for x. Now here, the way I say solve for x is I Sympy solve. I give it the expression, then I tell it what variable I want it to solve. So I say, okay, well, x squared minus 3y, solve for x gives me two solutions. Minus square root of 3 times the square root of y, and square root of 3 times the square root of y. If I say, well, you know what, I want you to solve for y, it's going to say, oh, okay, well, in that case, it's just x squared over 3. Now, whenever you have an equation here, and you say solve it, it always assumes this is equal to 0, right? So when I say solve x squared minus 3y, it's assuming, oh, x squared minus 3y equals 0, right? And you could explicitly say it. You could explicitly use this notation to say, hey, solve for this, and it's gonna, or I need to put a Sympy in. I think I need to put a Sympy in here. I think that's right. Or maybe not. No. Yeah, so here, for instance, again, it's the same thing, right? But here I'm explicitly saying this is equal to 0. And of course I could say equal to 6 and give me a different solution and it'll do that, right? So in Sympy, you'll generally use the EQ to have an equation with a left-hand side and a right-hand side. Using equality can be a little bit tricky because sometimes they might mistake it for an equality in Python. So you want to have like an EQ for that. Okay, we'll bring it back to its original form. So far so good? Now, so we can also use it to simplify our code. Yes?
Yeah. Can you show solving systems of equations?
I'm not going to show solving systems of equations, but we can talk about it a little bit later. I've got a more complicated version of this sheet, but I don't know if I do systems of equations. We can talk a little bit about it afterwards, because I think you can also just use the matrix packages. And Sympy actually does have matrix support, so I think he does have support for solving systems. Yeah, in this case I'm just doing this, but you actually have matrix support, so you should be able to do that in this. And we can look at it like afterwards at visitor page. So now we can also take these expressions or even take these symbolic variables and have them run through regular Python code and actually see like how we can simplify it for us. So here's sort of an example, and this is kind of like the sort of classic toy example of computing like compound interest, right? I've got a program, and I want to say, hey, I want to calculate the compound interest of some value. I've got a principal, I have a certain amount of time, I have a rate. What's my total return on my investment, right? And you can see right here, it does a very sort of, naive calculation, right? It's like, okay, let's loop over for my entire time period, which is n, and we'll just keep adding the interest accumulated to this principal over the time period and return value, right? And it gives me this. Okay, straightforward. A lot of people just code it that way in the loop. But let's say I want to say, hey, I want to see if maybe there's a better way of doing this. Well, so the nice thing about this is these values here, they don't have to be numeric variables. They could be Sympy variables. So I can say, you know what? I want to have the same thing here, this loop, but now I want T and R to be symbolic variables, okay? And I want to go ahead and just print out the total expression at the end. So I'm going to run this. And so you can see what's happening here. I'm saying, okay, look, let's loop over this. Give me the symbolic expression at the end. Now, you can see this really big, nasty behavior, right? I'm like, okay, well, what happens if I factor this? Let me factor this thing, okay? So let's do it. And now it says, oh, okay. So I'm like, okay, well, this is 10 periods, and it says t times the quantity of r plus 1 raised to the 10th power. Okay, what if I said this was 5? And I'm like, oh, So I'm like, okay, well now that I see the trace and see what it's actually computing symbolically, I'm like, I don't need this loop. I can just put in this formula directly and not have to deal with the loop, right? And in fact, if I don't want to see it as a sort of Sympy, but I want to see it more like Python, I could say, hey, print it the way, Python would have. Okay, cool. Then I can just take this, copy and paste it, and just use that as my function definition rather than loop, right? So that's kind of like an example of how we could use it to like see what's happening in a loop and see what gets accumulated, and then use it to help us both in testing and simplifying our code. Make sense? Questions? And yeah, here, all I did was the same thing here, right? We see that this variable, this 5, this period is just going to be whatever n is. So that's a new implementation. And we see here it produces the same result. No loop, simple expression. Right? And again, and I can even do it for testing, right? I can even use this to test. So for example, I can use the same sort of idea and try to test. So there's something called a dot product where you can have these two vectors, right? And you can basically multiply them and then sum the results of the product. So if you have like say W and X, right? And your vectors column arrays, right? It's more comfortable for you. I can say, yeah, I want to multiply W0 times X0 added to W1 times X1 and so on, right? So I kind of want to take this, and my dot product basically by definition is this expansion right here, right? This is actually the way we write it, right? The sum sigma Wi xi, and it expands out to this, right? W0 X0 all the way to that. Now, so I'm like, okay, well, so I've got this. So again, I've got this loop that basically just loops and does the dot product. And I want to say, hey, does this actually work? Now, normally when I'm testing something, a lot of times I'll throw values at it and see if the values are the results I expect, right? I'm like, oh, I know the dot product of these two vectors should be that, and this should be that. But I can also say, you know what? I want to do something a little bit more rigorous, a little bit more broad. Instead of actually throwing all these values at it, I want to use symbolic variables and see if the result is actually this expansion. Because if it is, then by definition, I know that this function implements this expression, right? So again, what I'm doing here is I'm just saying, hey, my W is now a sim array. A sim array is a way of telling Sympy, give me an array of symbols. So I have W and X, they're both symbolic arrays, right? And again, and here I just have a loop where I'm implementing my dot product. And then at the end of the loop, I'm just saying, print it out, right? And that's just going to be, again, an expansion. And then I'm going to just do this 11 times, and I'm just calling this function. And I'm taking a look here. Okay, so 11 times. So the first time I get 0, okay? If I have one element array, W0 times X0, W0 X0 plus W1 X1. And I can see here that this is expanded out to exactly what this expression is. So I can be like, symbolically, I'm like, okay, so symbolically, I know that this function actually is equivalent to this expression. Because now instead of throwing a bunch of spot values, I'm seeing that it builds up symbolically to what the expression should be. And that's like another way I could use it to do some symbolic testing of like, say, some code. Does that make sense? Questions? Sometimes it's pretty fun. I like Sympy. Yes. Oh, hand up, hand up. Yes. Go for it, Justin.
Why'd you get a 0?
Oh, I got a 0 here because the first time around, I was writing it on zero element arrays.
Okay, I'm disappointed.
Why are you disappointed?
Because you should have said that that's a degenerate dot product.
I like using the word degenerate. Well, I'll find a way to squeeze degenerate into our conversation. Don't worry. So.
Okay, thanks.
No problem.
That's a degenerate dot product. It's a sum of nothing. It's a sum of nothing.
Yeah, it's a sum of nothing, and so it amounts to nothing. So it's degenerate. Thank you for laughing. Thank you, sir. Thank you for calling me out on my irresponsibly not taking the opportunity.
Yeah, my pleasure.
Cool. So yeah. Now, so Sympy also, in addition to like factoring out expressions, it can also take a complicated formula, find repeated elements, and pull them out and give you a simplified formula with assignments for the repeated elements. It calls this basically factoring out common subexpressions. So give you an example here. So I'm declaring some symbolic variables, w, x, y, z, right? And here's a pretty hairy example expression. Not terribly hairy, but you know, right? W plus x plus y plus z times w plus y plus z divided by w plus x cubed. And I'm going to print it and I'm going to say, hey, factor out some of these common sub-expressions, right? So let's take a look at this. So of course this is my original expression, right? W plus x plus y plus z, right, over w plus x cubed. And this is my expression with the common sub-expressions factored out. So what it does, it says, okay, well, it's like first I notice that y plus z is repeated here. So let's call this x0. And I see that w plus x is repeated here. Let's call this x1. And then now that I have x0 and x1, here's your simplified expression using x0 and x1. Now it's like, oh, w plus x0 times x0 plus x1 divided by x1 cubed, where x0 and x1 are these sub-expressions. And so basically what it does is it finds repeated elements, assigns them to variables, gives me a new expression using these variables. And so I can use this if I have, like, say, a calculation in my code that I'm doing a lot, right? I'm like, well, I don't want to repeat these elements all the time, so let me at least recalculate some of the more expensive portions of it. And in that way, I have an expression that's both easier to understand, but also more efficient because at least these sub-expressions are only calculated once. So that's something where, for efficiency, assuming your code is so like runs through enough cycles that this makes a difference, and also for making your expression easier to read, you could use it and then just again set up these sub-expressions to simplify the expression. And with a much more complicated expression, you can see where this would really kind of come into its own. Does that make sense? Okay. Now, so in addition to all of this, Sympy also lets us actually find like a function that will match a truth table. So if you have, like, say, a bunch of like Boolean values, and you know they should evaluate to true, and there's a whole bunch of different sets of Boolean values, and you're like, well, what possible Boolean expression can make all of these true? Sympy can help you out. So let's do this first, but first let's talk a little bit about truth tables, just to make sure we're kind of grounded in what we need to talk about. So a truth table is just a table where you have all of your Boolean variables, okay? And then you have your last column has the result of some Boolean expression of it. And then that way you see all the possible values of the Boolean variables and the values of the operation. So I'll give you an example by showing you a truth table here, okay? So here I generated a truth table, right? I have values x, y, and z, and then I have this function here. Now, this function here is unspecified because we want to discover it, but it's basically some Boolean expression that takes x, y, and z. And so if you look at this Boolean truth table, it gives me all the possible values of x, y, and z, right? And I'm saying, hey, for all these values of x, y, and z, I can see that x0, y0, z0, I get a 1. When z is 1, I also get a 1, or true, right? 0 is false, 1 is true. And I see I also get a true when y is true. And then every other case here, I have a false. And I'm like, okay, so I know it's my truth table. It defines, and the truth table will define a Boolean function. Because, fortunately with Boolean values, you don't really need to like go through a lot of traditional proof techniques because you can enumerate everything. So I'm like, okay, well, I kind of want to know, that's really great and all, but what is this expression then? What is this f? How can I discover it, right? So what happens is that Sympy has something called minterms and max terms. And what minterms and max terms do is you can give them these Boolean values and their expected results that are for true, and they'll actually find the Boolean expression that actually will generate that. So now, when it returns the results, it'll return the results in what it calls CNF or DNF. So CNF just means conjunctive normal form. And all it means is your expression is returned to where you have, all of your sub-expressions can be ors, and then they're all connected with ands, right? So it's basically a conjunction of disjunctions. Or I can return it in DNF, which is a disjunctive normal form, which is like the opposite, right? You have conjunctions and they're all connected by disjunctions, ors. And they're both equivalent. It's really a matter of, do you prefer CNF, DNF, do you care, right? So here, and Sympy actually calls these POS, which stands for product of sums, or SOP for sum of products. But product POS is the same as CNF, and SOP is the same as DNF. So here, so basically what I'm saying is, I'm telling Sympy, hey, these are all the values I had here, X, Y, and Z. And I say, hey, these are my inputs, they're all my values for X, Y, and Z, okay? And these are all the true inputs, right? These are all the values that evaluate the truth, these three rows. And I tell it, give me the Boolean expression that will give me true everywhere this is true, okay? And then it's gonna give me false everywhere else. So when I do that, it says, sure, if you want it in CNF, not X and not Y or not Z will give you this truth table. And you can actually work it out if you want to convince yourself. Or if you want it in SOP, it's equivalent, just puts it in a different format, not X and not Y, or not X and not Z will also give you this truth table. So in this case, it's like I've got all of these values, and now it tells me what is this function that returns this and gives me this truth table. Now remember, it's going to give me values that are true here and false here. But I may sometimes only care about true values. I might say, hey, what are the values here that are true? And I don't care if these are true or false. I just want to match true values. So what I could do is I could go back to it and I could say, hey, I want you to go ahead and do this again, but this time, there's some terms I just don't care about, right? Like here. Here's an example of a truth table. I'm like, hey, I want these values to be true. I don't care what these values are, but this last one has to be false. And so these values that I don't care about are called don't care terms. So I can call it and say, hey, same call, but now I actually give it the rows I don't care about. I say, you can make these anything you want, I don't care. These have to be true, I don't care about these, anything else has to be false. Sure. Sure. Yeah, I just put asterisks there. And the only reason I did this was just so you have a pretty data frame to look at. Yeah, all this extra code right here is nothing but put it in a panels.
It could be any kind of character, as long as
Oh, yeah.
1 or 0.
Yeah, I mean, it's going to want to see zeros or ones.
If you put in U,
Oh yeah, it doesn't matter. Yeah, I just put in star because star usually means anything. Yeah, this is all just purely for display purposes, just so you have a visual to make it easier. Yeah.
anything that's not 1 or 0, it's U.
Yeah, yeah, anything that's not 1 or 0, I don't care about. So maybe it'll assign this to 1, maybe 0. Yeah.
I mean, the inputs, as long as it's not 1 or 0, interpret it
As a don't care, right? And in fact, all of these rows here, yeah, I pretty much put them in under don't care. So they're already in this variable don't care. Yeah.
Oh, so you have to specify.
Yes. Oh yeah. Like over here, you give it your true inputs, which I already set up earlier, which are all these values. The don't cares, which is this variable right here, and that's all these guys. Yeah.
Oh, so it's not, so it doesn't interpret the
Oh no. This is all purely for display.
Okay.
Yeah. It couldn't care less about this or this. Yeah. Sure. So that's your original,
Let's go down.
and that's
Yeah.
for all. Sure. Yeah. And again, all this is just to put it in a data frame. In reality, I can delete all of this and only just set up my true inputs and no cares. And when I run this, it gives me a much simpler answer. Because now that I tell it I don't actually care about all those other values, right? It can now give me a much simpler expression, which is, oh, in that case, you just want not x. And if you take a look here, you realize that, yeah, not x will give you this table. Not x, that's 1, not x1, not x1, we couldn't care less about any of these, right? So whatever. And then not x 0, right? Now, if this one also became a don't care term, then this would just give me an answer of true. Because at that point in time, it's like, true will give you everything. You don't care about anything else. Does that make sense? Do you have a question, Nick? Or?
No.
Now, so now, what's interesting about this is this actually came up at work. So I was actually at a role, and they had some data that they were pulling from a different vendor, and this data had product configurations. Okay, so it would have like, hey, is this product, for example, does it come in like large or not, yes or no? Does it come in different colors, yes or no? They had all these like Boolean flags, right? That had all these different configuration options for a product, and certain combinations of flags would actually lead up into certain like product bundles, right? True or false. It's like, oh, this is this kind of product. And so they used to get all this stuff from a vendor. And then one day they lost access to the vendor. They just had the data. I don't know if the vendor, what happened with the vendor, but they couldn't get it anymore. So they literally had all of these different product flags, and they knew that these combinations of Boolean variables, these combinations of switches, was supposed to give you membership in this product, but they had no idea why. Like, how did it all relate? And they literally used min terms and max terms to reproduce the rules that the vendor was using because they no longer could actually get it from the vendor. And then they use a different tool for it, but this was basically, but the tool implemented min terms and max terms and don't care terms. And that's actually what they did for the flags. Cool. Now, let's see how we're doing on time. We're doing okay. Yeah, we're doing pretty well. We got about 12 minutes ahead. So do you have any questions so far? Cool. So this was pretty much it. Now I do have a sort of director's cut of the sheet where I have a lot more. This is kind of the abridged version, but I can also like share.
Can you show us some of the system?
Sure. Yeah, and also show you. Yeah, but yeah, this one, yeah. So there's a longer one if anyone's interested, where I do eigenvalues and eigenvectors, and matrices. Like there's a ton to Sympy, linear regression, but I didn't want to kind of overwhelm the group, so I kind of gave you a director's cut. I can give you access to this sheet too if you want, including efficiency and a lot of stuff with like approximating functions and so on. So there's a ton more, and yeah, we're gonna go look up the solid systems equations. There's a ton more you can do, including Boolean satisfiability, that I kind of left out just to keep this talk from going too long. But if anyone's interested, I'll be happy to give them a director's cut of the sheets, and this goes into a lot more detail and even covers efficiency. But let's take a look and see. Let's see, Sympy systems of equations. Okay, what do they have here? Using Sympy, et cetera, linear and nonlinear. Okay. Hold on, okay. Okay, so they're recommending that we use and solve. So that's okay. And they have solve. Let's see, they have solve here. Okay, here we go. So here to give you a system of equations. So let's just. So you should pretty much just be able to, and let's go over to, let's go back to the top of the sheet. So over here, so pretty much over here, you just solve.
Like say you have three, you want to solve.
Oh, you want like a third one?
So say you have like a cubic polynomial equation. You want to find a coefficient square.
Okay, sure.
Yeah, you have three.
Okay.
Yeah, you have three equations.
Okay. Like 0. Something like this, you mean?
Yeah.
Let's see if we actually anything about here. Let's see what's going on. Oh, yeah. Remember what I said about the equals 0? Yeah, I could have put EQ, but then again, it assumes equals 0, right? So let's leave it here. There we go. So in this case, there's no solutions to this one, right? Yeah. If I wanted like an equal 0, that's when I would use the EQ, right? Forgot about my own rule, but in this case, yeah.
Plus one maybe?
I would, sure, do that.
Something is wrong.
You
No,
can't find it.
no, there's no solution to this. It says there's no solution.
Sure.
Do we have one? Do you have one where you know there's a solution?
It said x times 1, try x plus 1.
Oh, just x plus 1 here, you mean?
No, x plus 1. It's probably,
Oh, for this last one, x plus y.
yeah. X times y is probably giving it divided by 0.
No solution to this one.
Or just x plus 1. So x equals 1. Take it. X plus 1.
X plus 1. Nope, no solution. We can plug it. I mean, we can, yeah. We can see like there's. Let's see if they give us any.
It's tricky when you have three.
Yeah.
Okay,
Equations.
Yeah. Well, once you
Yeah,
have
I-
one, two terms, it becomes tricky.
So cubic equation of a plus b times x squared plus c times x cubed, and then you have the initial conditions when x is 0, a plus b plus a equals 0. Right? I mean like this type is a
Okay.
cubic polynomial a plus b times x plus c times x squared plus d times x cubed.
Like this.
Yeah. And when x is 0 then it's equal to when x is 0 say it's equal to. So basically
Here you go. Here's your answer.
you want to solve for the coefficients a, b, c, and d. You don't care about x.
I mean, you want A, B,
So
C, and D?
when x is 0, then basically a equals a, I guess.
So you just want to solve for these?
Yeah. Now solve for coefficients. Okay, so when x equals 1, it just a plus b plus c plus d. Right?
Let's see.
So that's the function, right? And let's say when x is 0, the function is equal to 2. So basically it would be a. So basically a equals -2. That's one system equation.
Okay.
So a minus 2. That's the first. Type that in for your first equation.
So okay, and you want to keep this guy here?
Yeah, create some add a comment. Add a pound. Create a new line.
Oh, you know, okay.
Create a new line. No, keep that. You want to add a comment.
Yeah, you want to keep that, right? Or you want? Or wait, do you want?
Add a comment. Add a comment to it.
Like
Add a
comment
new-
where?
Yeah. So in the comment say x equals 0.
Oh, you mean at the end of the line?
Y equals. No. Delete that. Create a blank line.
Okay.
Okay, comment. It's a comment line. Okay, when x equals 0, y equals 2. Okay, and then next one, when x equals, let's say 1 at the other end, y equals 2 again, let's say.
Okay.
And then when x, the midpoint, when x equals 0.5,
Mm-hmm.
y equals, let's say, 5.
Okay.
Then E4, right? And then in the last equation, okay, at the midpoint, when x equals 0.5, you want it to be flat in the middle, so you want the derivative to be 0. So the derivative of that would be anyway, then derivative of y is equal to 0 at the midpoint. Now put those equations in. So the first, when x equals 0 and y equals 2, that would mean you just have a, right? So it's the first equation would be a plus 2, a equals 2, so a minus 2,
Okay.
right? Second one, when x equals 1, y equals 2, that would mean a plus b plus c plus d equals 2, right? So a plus b plus c plus
Minus
d
2.
minus 2
Mhm.
is equal to 2, right? Okay. And the next one's 0.5, right?
Mhm.
So that would be a plus 0.5 b.
A plus 0.5 times B.
Yeah, plus c times 0.25, right?
Okay.
Plus d times 0.125.
Okay.
And then that's minus 5, right, equals 5. Yeah.
Okay.
And the last one is a derivative, so that would be yeah, that would just be b plus 2. Let's see. Yeah, b plus 2 times 0.5 times x.
Like so.
Yeah, plus 3 times c. Sorry, no, sorry, it's b plus 2 times 0.5 times c. That's times c.
Like so.
Plus, yeah, plus 3 times 0.25 times d. Yeah, that's it. And you want to solve for a, b, c.
B. Okay, here we go. Here's the solution.
And those are your coefficients. There you go.
No problem. Any other questions? Yeah, so yeah, it could do a fair number of things. Yeah. Cool.
Great.
Yeah. So yeah, that about wraps it up. So again, you've got the links to this. If you have any trouble accessing the collab sheets, let me know. I'll make sure you're set up. But I've got the link in LinkedIn. I can email you the link if you can't get on LinkedIn. And that's going to give you pretty much what we did here. I'll just go ahead and kind of leave it here as a little Easter egg for anyone who comes along. And then, yeah, and if anyone's interested, I can give you access to this much longer one that I was kind of just playing around with. And of course, it's got a lot of documentation. I mean, the stuff that I showed you just scratched the surface. I mean, there's function approximation, there's like interpolation, there's a ton of stuff that I didn't do. There's a bunch of probabilistic models in here. You can see right here, there's, in fact, you know what? Let me just go to the Sympy in general, just give you a quick idea, because like I said, this is just a very broad introduction, but there's a ton of stuff here, right? You've got, see right here, you've got your whole API reference, which tells you a lot of stuff. It'll do code generation, and so on. So, like I said, if you're interested in this, by all means, go through the documentation. I only scratched the surface. But yeah, that's pretty much Sympy, and yeah. But yes.
I did have a question. I might have missed it, but the expressions that it gives you as output,
Mm-hmm.
can you then take those expressions and treat them as functions, like pass values to them and get?
Yeah. So Sympy has two ways of doing that. So one, you've got something called subs, where you can actually tell it, hey, substitute this value for this variable. And I didn't show it in my sheet, but I think I've got it in my director's cut. So let's see. So subs, yeah. So yes, you can do like subs, where you can basically say, hey, for these particular values, for these particular variables, put in these values, and then give me the solution to that equation. So you can use subs to do that. And you also have something called lambdafy, where you can actually tell it to like take your expression, turn it into like a Python lambda that uses NumPy, and then you just feed it values. And in fact, if performance is a concern, use lambdafy, because Sympy is great, but Sympy can be slow. But if you already got like the expression you want out of Sympy and you're ready to use it, tell it to lambdafy it, then use that, and it will run orders of magnitude faster.
Okay.
So you got two ways of doing it. Yeah, you got subs, and then you've got like lambdafy, which can also take an expression and turn it into a lambda, and then you pass it values just like you would any other function.
Okay. Okay.
Yeah, and this one's on a director's cut sheet, but I can definitely provide this sheet as well. It's just a lot longer. There's a lot more to it, but yeah, you can absolutely do that, and both ways will work. But subs is like the easy way. If you just want to just plug in, substitute certain values for the expression, you could just say, hey, subs, and then it'll recalculate the expression with them. And you don't have to substitute everything. You can like substitute only one or two variables and have it simplified to that, or you can substitute all of them, and then it'll calculate out the formula. Yes. Did that answer your question?
Yeah, no, definitely. This, yeah.
Sympy's pretty sweet. And there's a lot of stuff built on Sympy too. If you ever heard of Sage and Python, I think they built it on Sympy also. So it's a very nice package.
If you give it a period, how would it solve?
I don't know about solving periodic. Huh? Yeah. I don't know about solving periodic functions. I mean, that's something we can play around with. The only thing I know with periodic functions was play around with like interpolation and approximation. But that was like other stuff I was playing around with. Yeah, and I know it has heuristics for solving certain types of things.
Like just a string, or for just a sign of X.
You wanted to solve, okay, let's solve. Okay, so you want to solve,
Sign of X.
okay,
I always find these people
Sign of X.
are looking
And then,
but I was trying to catch some things. But this one kind of
just sign of X,
so
X
he
minus
basically
0.
kind of trying to gaslight
Everything
into
will be right.
going crazy
like this.
by because he has things on it where he's like, oh, I should not let people disobey the law. So if I tell them that that's the law, then he starts going,
Well,
oh,
here's a 50
no,
one,
you
you
need to
can
worship because that's the law. But
Okay, well,
it just
okay,
I
so
hate
it's
it
telling me
because
there's no solution to this.
Should be.
it just knows out. Yeah, but like it's still kind of sad, but it's like I'm not gonna continue, which I hate. I think they have like another model that is looking at the conversation. It's like
This one.
this doesn't sound
too
right.
close.
So we take that out to get a 0, we get a pi for the values for X.
Those numbers
Oh,
like,
yeah.
oh, hey, I have this
What you
really
wanted.
bad like mental problem where if you use more than
I
3
see,
models
it's
in
solving for,
conversation and then
solving
get
for a
it.
sign of X equals to 0.
Yeah,
Log,
because if you don't have that, it's gonna
Right.
serve. I mean, if you wanted to put an E,
Something
like
like
EQ, like if you
It's
wanted
like,
to,
oh,
we could do like.
sorry about that, and they use like a smile emoji.
Like sign of X,
I'm
that's
sorry,
sign of
sorry.
X.
It's like, oh, I'm sorry, I didn't mean to do that, and then it's another emoji. It's like, oh
I
my
know.
god, I'm sorry, I'm really didn't want to do that. It's like,
Yeah, X squared.
I'm actually joking, I don't really care if you die, and it
But
starts
there will be plus or
spamming
minus,
emojis.
plus or minus.
Yeah.
They
Zero.
keep catching it.
No, X
So I
squared,
never catch it when it's like,
minus 4.
That's what happens.
X
on
squared minus
Friends
4.
models on
Just
Reddit.
that one.
Oh, just X squared
it
minus
just seems
4.
like the
Should
same
be
thing.
plus or minus
No,
2.
it's like, I remember like when like
Yeah,
sign
plus or minus
contract
2.
where they allow specific companies to train models using their data like officially. So like people were like, okay, now I'm just gonna randomly say the same everywhere so that it learns
Wait, what
to
did you
say
get
that.
for sign of X?
For sign of X, it gave you 0 pi.
So just give you solutions equal to 0.
Cool. Yeah. Awesome. Well, yeah, that wraps it up. So thank you very much, and hopefully see you folks next month. Might be doing, I think I might be doing stuff on invariance and automated testing. So yeah, I'm still gonna working that out, but that's probably gonna be the topic for next month. Cool. Thank you. Yeah, and then hang around here.
I didn't know about this one.
Huh? Yeah, Sympy is awesome. Sympy is really nice. Yeah. Thank you. Yeah. And again, if you want a free like mathematical like language, GNU Octave is really nice too.
So,